these should be the graphs you generally got. So remember, with absolute value, we just picked out the h and the k value as our vertex. So -1, -2. And then we used the 2 as the slope of the side. So we didn't have to use transformations as much in the absolute value because it's linear, and so we get to use that slope idea. In the other two functions, we really had to use what the parent function looks like and then do the transformations. So in the quadratic here, the transformations is that there's a translation 2 to the right and 3 up. That's why you see the vertex at 2, 3. Okay. The only other transformation is that rather than facing upward, it's been reflected so that it faces downward. So I used the same pattern of points from the parent function, but downward. So 1 away from the vertex was 1 below it. 2 away from the vertex was 4 below it. And then, like we talked about yesterday, our parent function for our square root. The only transformations here are translations. So they're basically just kind of changing that starting point of our graph. But once you find that starting point, all the points are the same as they would be in the parent function from that position. Okay? So +3, -2 is our vertex. 1 away from that would be 1 above, and 4 away from it would be 2 above. Okay? Is this all right with everybody? All right, so we have these graphs. So then I want you to look at what it says right below that on your handout. So it says in graph number 1, highlight the portion of the graph that is in the domain x is less than 1. So in a different color, really bold, or with a highlighter, you want to highlight the portion of this graph that is in the domain x is less than 1. And then it says in graph number 2, so here we want to highlight the portion in the domain where x is less than 1. So you're actually highlighting the part of your graph that meets this criteria. The x coordinates are less than 1. Okay, it's in that area of the domain. For the second graph, it says in graph number 2, highlight the portion of the graph that's in the domain where 1 is less than or equal to x is less than 4. And then for the last graph, it says in graph number 3, highlight the portion of the graph in the domain where x is greater than or equal to 4. So try to identify which parts of these curves, okay? So literally just on the curve, identify the part of the graph that meets this requirement, okay? So I'll give you guys a second, and then we'll do it up here also, but I want you to think about it for a sec, okay? The domain where x is less than 1. So on the x-axis, here's 1, okay? Sorry, I have my highlighter function on, okay? So less than 1 would be to the left of that, okay? So that's basically where x is less than 1. But I want this graph when x is less than 1. That means all of this part of the graph would be included, this part of the graph would be included, but I would stop there. Is everybody okay with why I would stop right there? Okay? And this graph would keep going this way, okay? Because that's still when x is less than 1. But if I only wanted this portion of the graph in the domain where x is less than 1, that means I would stop right here, okay? But I would go to the left forever because all that is still less than 1. Is that okay with everybody? So I'd kind of like cut the graph off right there. Okay? So if the second graph, I want the portion of the graph where x is between 1 and 4. So that involves kind of two pieces of information, between 1 and 4, okay? That's where 1 and 4 are on the x-axis. So think about the parts of your curve that line up with that. So that's from here on the curve, around until there, and that's it. So if I only want the part of this graph that's in the domain where x is between 1 and 4, I basically just want this little part of the parabola right here that I've highlighted. Does that make sense to everybody? Yeah, Stephanie? Good, and we'll talk about how to do the endpoints in a minute. Good, okay, so I'm glad you noticed that. This says less than, not less than or equal to, so we'll talk about the endpoints in a minute, like how do we get right up to there but not actually include it, okay? All right, and then in number 3, we want this graph, but only when x is greater than or equal to 4. So 1, 2, Here's 4 on the x-axis. To the right of that is when x is greater than or equal to 4. So on the curve that I've drawn here, that means I would kind of start here, and then I would follow the curve this way, and I would keep going because there's no limitation on how far I can go. I just have to be greater than or equal to 4. Is this okay with everybody? All right. All right. So the idea is, if you want to make a graph like we saw in the graphing stories things, where you have different shapes occurring at different times, this is essentially what you have to do, right? Maybe this is the shape you want to use in part of the graph, but you only want to use it in this part of the graph, so you want to cut it off at this certain spot. Maybe you want this shape to happen, but you only want it to happen in this part of the graph, so you have to cut it off at these different domain parts, okay? Some limitations on x. Same thing over here. Maybe I want this shape, but only from here forward. And maybe I want all of those on one graph together, right? So how do I get them on one graph together? You know that mathematicians aren't going to sit here and do what I did for you, like, please graph these 3 graphs. Then go highlight from each graph this part of the domain. That's way too many words, right? We have notation and stuff like that for everything. So what you see right below that is how we would actually note what we wanted you to do. So I want to copy this for a minute. All right. So what we would do as mathematicians, if we wanted you to make those 3 graphs, but only use those specific parts of them and then put them all together as one graph with all these weird shapes together, what we would do is we would write an equation like this, okay? So notice that this equation, instead of being one equation like you're used to seeing, it's technically one equation, but within the equation it has 3 different pieces, okay? So they call this piecewise functions, because instead of being one complete function where one equation tells you everything to do, multiple pieces tell you, well, graph this, but only graph it on this part of the graph. And then on the next part of the graph, please graph this other shape. And then on the next part of the graph, please graph this other shape. So notice that in the piecewise function, the amount of pieces there are represented by the amount of equations you kind of see written in there, okay? And then notice that next to the equation, they write this. This was like the part where I said, go highlight that part of the graph only when x is less than 1, right? And we talked about kind of like throwing away the rest of the graph and cutting it off. Instead of writing that all out in words, they say, hey, graph this only in this area. Graph this second piece only in this area. Graph this third piece only in this area, okay? So basically, if we wanted to build the graph of f of x, this function that looks crazy because it has all these different pieces in it, we're going to take everything you highlighted in the graphs above and put them together into one graph, okay? So we want this function only when x is less than 1. Look at what we highlighted where x is less than 1. Put that portion of the graph onto our final version of the graph. So I'm going to put that much of that function, okay? Now, to get to Stephanie's question that she asked about, this only says x is less than 1. So right here where x is 1 and I'm trying to end the graph, what kind of endpoint should I have there if it just says x is less than 1 and it doesn't say x is less than or equal to 1? An open circle. So this graph needs to end here with an open circle. Okay? Then I'm going to go and put the next portion of graph connected to it. So the next portion of graph I want to exist from 1 to 4, and I want it to be this quadratic that we graphed. Basically, we already graphed it and highlighted the portion that we want. So now take that portion of the graph and plop it on your graph next to this branch. Now they happen to share this point at 1, 2, and on this graph, x can be equal to 1. So now this point is going to look like it was never open because you had an open point there, but then you had a closed point there. So is that point eventually covered on our graph? Yes. So it's just going to appear as though it's covered, okay? So there's that portion of the graph. Oh, how should my endpoint look there at 4? open because here x is only less than 4. So let me correct that. Okay. All right. Now the next portion we want to draw this square root graph, but we only want to draw it starting when x is greater than or equal to 4. So only the part that we have highlighted. It happens to also have this point at 4, -1. So again, that was open, but now it would appear closed because the other graph sits on top of it. And then we would have some other points here, and it would go like that. So this is how you graph a piecewise function. Are there simpler ways than literally graphing every part separately, highlighting it, and then putting it together? Sure. But is that a good way to understand what this is telling you to do? Yes. And now that you understand, if you have a quicker way of getting this graph, that's perfectly fine, and we'll look at some ways of doing that. But if all else fails and you're getting confused, go graph each thing separately, like you know how, and just like think about the part you want to put on your final graph, right? So if all else fails, you have a method right here. It's long, but it works, right? So you can always go back to that. And then while we do one of the examples today, we'll do some other methods so you guys can see faster ways of getting that on the graph, okay? All right, domain and range of this function. So what is the domain of the function? All real numbers. We can plug in whatever we want. How would the domain not be all real numbers? How could they have changed the function so that the way they wrote it over here to prevent the domain from being all real numbers? Nicole? Yeah. So they would have to change like certain parameters over here so that you couldn't plug in any x. Right now we can plug in any x, right? If someone gives you an x to plug in, let's say I wanted you to plug in 8. Which piece of the function do you plug 8 into? First piece, second piece, third piece? If x is 8. Third piece, because the third piece is when x is greater than or equal to 4. Am I allowed to plug 8 into the second piece? No. So, little side note right here, if somebody asked me for f of 8, okay, so your homework will ask you for something like this, you can't just plug it into all of the pieces, okay? Sorry, no go. You have to actually think, where does 8 belong in this function? It is an x value that's greater than or equal to 4. It belongs here, and then you would plug 8 in there, okay? And if I plug 8 in there, 8 minus 3 is 5. So basically, I get rad 5 minus 2. Without a calculator, I would just leave it like that, okay? All right, so our domain is all real numbers because they didn't do any restrictions here that would stop us from plugging in any x. There's a place for every x to be plugged in one of these pieces, okay? What about our range? And looking at the graph is really going to help you guys with that, okay? Zeke? Good. So y is greater than or equal to -2. See how -2 is the absolute minimum that our graph reaches? It doesn't go below that, but it continues to rise above that. I don't care that many things were overlapped. I just care overall what values is it reaching up and down, okay? All right, so let's see a way that we could graph these without making all 3 separate graphs if we wanted to, okay? But is the idea okay with everybody? So this is a piecewise function. This is how it works. Okay. All right, so this function has how many pieces? 2 pieces, okay? So you expect kind of 2 different shapes to show up to create this curve on your graph. What shapes are they? The first piece, what shape? Linear. Second piece? Quadratic, okay? Where do we change from one graph to another? When x is 0. So sometimes the way I like to think about this, okay, this is not part of my graph, okay? This is my thinking process. I like to think of like, okay, this is where I'm going to change my function, and I can erase this line at the end. But this is if you don't want to graph everything separate and then highlight it and put it together, here's what you can do. Okay, so that's kind of the barrier, right? What's being graphed on this side of 0, on the left side? The line or the quadratic? Which one is being graphed when x is less than or equal to 0, on the left side of 0? The line, right? So on this side of the graph, I'm going to graph this equation. And when it ends at the barrier, should its endpoint be open or closed according to the domain restriction? Closed, because it is allowed to be exactly equal to 0. And then I kind of just write this for myself, like, oh, that will happen there. Okay? This is me. This is how I do it when I do it separately, just to help myself organize information. You're going to do enough of them that you find your own way to be helpful. Okay? All right, which means once I get past 0, when x is greater than 0, is when I'm graphing the parabola. And it's going to have an open endpoint at that barrier. Okay? So I did that stuff in yellow. I'm sorry if it's hard to see. I did it because it's my thought process. It's not actually part of the graph, and I wanted to make sure that you guys understand that. Okay? All right, so what's the best way for us to graph a linear function in slope-intercept form? What do you guys want to do? Okay, so find the y-intercept. The y-intercept is 1. That's going to be right here. That's on my barrier. So is it an open point or a closed point? We have to pay attention to that when it's on the place we're going. Closed, because we paid attention to that when we wrote that down, right? So at 1, I get this point. Okay? What's the slope of my line? 3. So from the intercept, I'm going to go up 3 over 1. Now, if I go up 3 over 1, is this a point I actually want included on my graph? No, because I just went on the other side of the barrier, right? If you have to do that, that's fine. But use that to draw the line and then erase the part of it that you don't want, okay? Because you don't want this graph to show up on that side, right? That's violating what it says to do with the pieces. Or just adjust it so that you're going down 3 and over -1 so that you can see it that way, okay? You know I can't draw a straight line, so I'm going to do all this action. Okay, so there's that branch. This point shouldn't really be on that side. Okay. All right, so parabola. Where's the vertex of the parabola? Zeke? 0, -2, because the only transformation is to go down 2. So 0, -2. Again, that's on the barrier. Open or closed point? Open. Okay. Are there any other transformations for this quadratic? No. So it should follow the normal pattern, which means you can go 1 away from that vertex in either direction, and you should have points 1 above. But I'm not going to draw the stuff on the left side because that's where the line is going. I only want the parabola graphed on the right side, so I'm only going to graph that portion of the parabola. And 2 away from the horizontally should be 4 above it, and then I get my curve. Okay? So that would be the graph of my piecewise function. Is this idea okay with everybody? All right. Again, if this is too much, like, oh, I can't do it that fast, graph them separately, highlight the parts you want, and put them together. You can use that first method that we used each time. Okay? Stephanie? No, so they're not always connected. It just depends. Last time they were connected because when we ended one and started the other, the endpoints happen to lie at the same position on the graph. Sometimes that will happen and sometimes it won't. And so you could have portions that are disconnected. Like we saw with the ponies, right? We had step functions. Those were actually different step functions, and they wouldn't have been connected because they would have started in different places and then had different lengths. Okay? All right. We will kind of use this one. The domain in that one was still all real numbers, okay? And then the range was all real numbers also. I don't want to worry so much about that right now. I just want to be able to make the graphs first. Then on Monday we can talk a little more about the range. Let me see if I want to do this one or a different one. Hold on. Okay, let's do this last one. Okay, how many pieces? 3. What types of functions are they? First piece, linear. Where does this piece exist? Read what the domain says. X is greater than or equal to -2 and less than 0. So that piece needs to be between -2 and 0. Okay? So between -2 and 0 will be that piece. Okay? Okay, second piece. What shape? Quadratic. Good. Where? On the graph. Okay, other way around. Greater than or equal to 0 and less than 2. So between 0 and 2. Okay, last piece. What shape? Linear. And it's going to exist between 2 and 5. A little squishy up here for my graphs. Okay. So first piece, line, y-intercepts at -2. Open or closed point for the y-intercept. The y-intercept is on the x-axis. It's when x is equal to 0. In that first piece of graph, are you allowed to be equal to 0 for x? No. So its y-intercept should be open. Okay. And then the slope of the line is 1. Okay. I could go up 1 over 1 and put a point right here. Am I going the right direction right now to draw my line in? Is that the area that my line goes in? No. It goes over here. So instead, I should probably do down 1 over 1. Okay. And it can be equal to -2, so its endpoint will be there. Okay. Let me erase the point that's not necessary. All right, between 0 and 2 is the parent function of the quadratic. So the vertex is at 0, 0. Is this branch of the graph allowed to be equal to 0? So second piece, can x be equal to 0? Yes, look at the inequality. X can be greater than or equal to 0, so that's there. Now, which part of our parabola are we going to draw? Good. Only the right side that's between these two things here. So 1 over is 1 above, and 2 over is 4 above. Now we're on our boundary at 2. For this second piece, is x allowed to equal to? No. So when I plot that point, open point. Okay? So there's the quadratic part. Okay, last is -x plus 6. This gets a little tricky. If you want to graph the y-intercept, it's over here, but that's not supposed to be anything that's graphed over here, right? That's like this point should not be here. I only want the line over here in this section. So my advice to you, put that there, and then start using the slope till you get to the section you want to be in, right? So my slope is -1, so I'm going to go down 1 over 1, down 1 over 1, down 1 over 1, down 1 over 1. Oh, wait, I'm in my section. Okay. So here, and then down 1 over 1, down 1 over 1, down 1 over 1, and I'm not allowed to equal 5, so it would be like this. And then I'm going to erase this part over here that wasn't supposed to actually be there. So you can still graph the line how you normally graphed the line, just erase the area where it's in a zone that it's not supposed to be in, and only keep the portion that's in the domain restriction that you want. Damien? They don't have to be connected. So it just depends. Oh, did I count wrong? Oh, yeah, I did. I started at 7. Thank you. I'll fix mine. Thank you very much, Damien. No, good. Thank you. That's what you're supposed to do. Okay. Is this all right? All right, so your homework tonight is a handout. It's basically going to ask you, it's going to give you some piecewise functions. It's going to ask you, like, what's f of 3, what's f of 5. So, small reminder, when they ask you f of something, pay attention to where you're plugging it in before you get your answer, okay? And then it's going to ask you to graph some piecewise functions, so just like we did here, okay? If all else fails, I don't want you to come in and say, Ms. Dahl, I couldn't do anything. If you're going to come in and tell me that you struggled, the work I would expect to see from you is that you tried to graph each piece separately and mark the pieces that you wanted from those and put them together on a graph. Because if you didn't try that, that's what I'm going to revert back to. If you don't understand the faster way of doing it, do it this other way. If you haven't tried that other way, I don't think you put forth the full effort. And I'm not saying that in a mean way. I'm saying it takes longer, but it can get you the answer. So if you're not okay with the way we just did it, you need to go and do it that other way. And that's completely okay, but it needs to happen so that you can get the problem done.